Brilliant. Okay, so we'll get started. All right, so we're actually just going to look at what acids and bases actually are. Okay, so very, very basic kind of introduction to them. So acids, they taste sour. Okay, we're going to be looking at different measurements of acids and bases. Okay, so when I say that blue litmus paper, we use this as an indication of acid and base. I'll get to that in a little bit later on in the lecture. But all you need to know for now is that acids, they turn blue litmus paper red. Okay. And what we're going to look at is that they react with bases in a neutralization reaction. Okay. So once we do, and what we do in the lab practical when we do our titration, we have an acid and we have a base, and they'll neutralize each other to form a salt in the water. So just general properties first, they're very reactive with bases due to that neutralization reaction. They turn blue litmus paper red, so this is kind of an indication that we use in the lab a lot. So we dip the litmus paper in, a blue litmus paper, if it turns red, we know it's acidic. And then some general properties of acids, even though you wouldn't be drinking the acids in the lab, more general acids taste a bit sour. All right. So prime examples of these would be things like citric acid and ascorbic acid and vitamin C. So you found these in orange juice. Okay, so if you like lemons contain a lot of citric acid, it's quite sour tasting. We also have gastric acid or hydrochloric acid in our stomachs. Okay, so this aids the digestion of food once it reaches the stomach, breaks it down into its more simple molecules so that it can be absorbed through the small intestine. Okay, so gastric acid brings about that kind of breakdown or decomposition of our food. All right. Another prime example would be carbonic acid. Okay, so this is added into kind of fizzy drinks like Coke or Fanta to stimulate the nerve receptors in the mouth. Okay, so it kind of gives it that like kind of tingly or bubbly feeling. That's the carbonic acid in the juice or the fizzy drink itself. So carbonic acid is converted back into carbon dioxide once the can is open. So that's why you hear that kind of the sound once it opens. So the pressure is released. The carbonic acid is turned back into carbon dioxide, and you have all the kind of bubbles within that fizzy drink. But that's resulting from the carbonic acid. On the other hand, then we have bases. Okay, so these taste kind of bitter in comparison. Okay. On the opposite scale, then, so if we're testing whether a substance is acidic or basic in the lab, we would use both red and blue litmus paper. But red litmus paper turns blue in the presence of a base. So that's kind of our first kind of indication of whether it's acidic or basic. We use two different the litmus papers. Depending on the color change, we know which one it is. Bases, if you actually get them on your hands, they can feel almost like soapy or slippery. So what particularly strong bases, and this is why they're kind of so dangerous and why we should always wear gloves when we're dealing with strong bases, is that they can actually react with the fatty acids and your cell membranes. So if you did unfortunately get a strong base on your skin, you would feel almost like a soapy or slippery feeling on your hands. Okay. What that is that the base is actually reacting with your cell membranes and starting to break them down. So obviously the stronger the base, the more likely that is to happen and the more reactive it is. So you'll see it in the lab, but we kind of have a lot of different safety precautions around both acids and bases, depending on how strong they are. But for that reason, okay, because they're very, very reactive with our skin. On the other hand, then, so bases and on the opposite side, they react with acids in that exact same neutralization reaction I was talking about. Okay, so acids will react with a base. On the same hand, bases will react with acids to neutralize each other. Okay. So bases are typically used in soap. Okay, so that reaction I was talking about on your skin, so that it starts to break down your phospholipid bilayers and your cell membrane. But bases are actually used in the production of soap for that exact same reaction. Okay, so not to get too much into it, but soaps are made up of triglycerides. Okay, so they're kind of in different components. What the base does, it breaks down those triglycerides into a more manageable section for the soap, and then the sodium hydroxide or the base adds to the molecule that's broken down to form soap. Okay, but it's the exact same reaction as if you had gotten it on your skin. that kind of decomposition or that breakdown reaction. For the same reason, then bases are often used in oven cleaners, okay, because they're very capable of breaking down the kind of grease and grime that builds up on ovens or in drains during that exact same reaction. Okay, so the breakdown of fatty acids, the breakdown of the phospholipid bilayers of fats. Okay. A very common example of a base would be ammonia. Okay, so you'd often see these in the toilet cleaners. It's listed on almost every toilet cleaner on the supermarket shelf. Okay, so ammonia is one that would be used most often in cleaners, and it's also met with that kind of very strong, very pungent smell. So you'd know ammonia just by the scent of it. Okay, so a couple of definitions of acid and bases then, okay? So there you'd see if you looked up the definition of an acid and base online, you would meet primarily three main definitions of that. And it depends on the solution that they're in. Okay. So but they all mean the exact same thing. Okay, so the Arrhenius definition of an acid or base, this is kind of subject to an acid and base being in water. All right. So an acid will produce a hydrogen plus ion, and a base will produce a hydroxide or an OH minus ion. The Bronsted-Lowry definition of an acid or base, so this kind of is more general, so this is in any solvent, it's not just water. But in the exact same way, acids, they donate a H plus ion or a hydrogen ion, bases accept a hydrogen ion. The Lewis definition of an acid and base, then, that's kind of more subject to organic chemistry. Okay, so we're not going to use that at all. We're going to kind of more focus on our Bronsted-Lowry definition. But just so you know, that the Lewis definition of an acid or base is that acids accept an electron pair, whereas bases donate an electron pair. But for now, we're just going to focus on the Bronsted-Lowry definition. So basically, if you see any reactant or any compound that is donating a hydrogen plus ion during a reaction, that's an acid. And any reactant or reagent that's accepting a H plus ion during a reaction is typically a base. So that's all we need to know for now. Is everyone okay with that so far? Okay. Okay, so we kind of have a couple of different methods that we use to detect an acid and base, okay? So I'm going to go through a couple of these in a second, but the one that's most important to us and what we're going to use in the lab on Saturday is what's known as an indicator. So an indicator is either a solution or a substance that changes color in the presence of an acid or base. So it's incredibly visual, okay? So it will be one color in a base, you put it into an acidic environment, it will change color, and we'll be able to see that change, and vice versa. So, like I said, we're going to be using indicators in our lab on the 25th of October. Okay, so this Saturday. So we're going to be doing a couple of different titrations where we will see that reaction between the acid and base. It will reach a certain point, or what we call the neutralization point. At that neutralization point, there's a big jump in and I'll get to that, the pH scale, but whether the solution is acidic or basic. So that will change substantially at that neutralization point, and our indicator will change color in corresponding to that. All right. So just going through it. So your first your first pass of an indicator or for the detection of acid and bases is a litmus paper. And like I said at the very start, so an acid will turn blue litmus paper red, and vice versa, a base will turn red litmus paper blue. These are kind of a first pass indication of whether it's an acidic or basic substance. All right. So sometimes we need to know exactly how strong the acid or base is for certain applications. But if we are kind of met with an unknown solution, we don't know what it is, we don't know how acidic or basic it is, we use this as a first test, and then we can determine, well, we definitely know it's an acid, and we definitely know it's a base. We don't know how strong they are, but at least we know how we're going to deal with it further, because we know what compound it is. For us then, for more acid and base titrations, we use a solution of an indicator. Okay. So as I was talking about there, the point of neutralization. Okay, so what we'll see on Saturday is that our acid and base will start reacting with each other. But we are using colorless acid and bases. Okay, so you'll see we're going to be using hydrochloric acid and sodium hydroxide definitely, but they are colorless. Okay, so there's no color change observed there. So it's actually very hard to predict where that point of neutralization is because we can't see it. Okay, so we're dealing with two colorless reagents. They're going to react to form a product that's also colorless. So we can't see it. So what we do is we add in a couple of drops of an indicator solution. So for example, if we add them to a beaker base, it will be one color. We start adding the acid slowly into that beaker. They'll start reacting with each other. The color will start to change, and then we'll see a really sharp change when it becomes more acidic. And that's how we know we've reached that point of neutralization. So I'll just show you this video. So this is actually the indicator we're going to use in the lab. So it's called methyl orange. Okay. So you'll see it there. The person who's conducting this experiment, they're testing it in water and a base and an acid, and you'll be able to see how the methyl orange changes color in response to that environment. Okay. So in water, that's a neutral pH. It's neither an acid nor a base, so it's going to stay yellow. In a base solution, then it stays that yellow color. Okay, so in a basic solution, it's yellow. And once he adds it to the acid, yeah, you should see that color change there. Okay, so it turns almost like a bright orange color. Can everyone see that there, yeah? Perfect. So that's what I'm talking about. That we'll see that in the reaction on Saturday, that it's in one basic environment, it's a yellow color. We start adding the acid slowly to it. We'll start to see the color change start to shift. And all of a sudden, at a certain point, we'll reach the neutralization and it will start turning that bright orange color. So it's a really visual way of interpreting what environment we have, whether it's acidic or basic. Is everyone okay with that so far? Okay. Okay, so how we actually measure the strengths of acid and bases then. Okay, so you may have seen this before or maybe come across the pH scale before, but it's a very visual way of looking at how strong an acid or base is. So for example, right, our litmus paper, like I said, is a very approximate test on on how strong an acid or base is. We'll know it's either acidic or basic. Basic is also called alkaline. Okay, so if you see alkaline anywhere, that means it's basic. But what a litmus paper will do, it will tell us whether it's in this range or whether it's in this range, depending on that color. But it won't tell us how strong it is. Okay. So we have to look at what the pH of it is. And the pH is a scale that we use to measure the strength of an acid or base. So the pH basically, okay, so pH is related to the hydrogen ion concentration in a solution, okay, and it's measured on a scale of 0 to 14. So the way we break this down is that the pH is directly related to the amount of H plus or hydroxyl ion concentration in a solution, okay? So if the H plus concentration is much higher than the hydroxyl or the OH concentration, our material is acidic. Okay, so it's within this range. We have a lot more H plus ions than we do OH minus ions. Conversely, then, if it's a basic solution, our OH minus concentration is much higher than our H plus concentration, and we're in this range here. Our 7 is a neutral pH. Okay, so our blood and our tears, they're all of a neutral pH. Okay, so our tears are around pH 7.4, the same as our blood. Whereas, say, the gastric acid that's in our stomach that helps the digestion, that's around a pH of 2. So we're well into the acidic region there. Okay, so a very, very strong acid. The bases that I mentioned at the start, so things like your drain cleaners, ammonia, would be more along the strong base range. Okay, so you're talking maybe 12 to 14 there. So just as a quick recap, this is all kind of tied to acid and base dissociation. So I mentioned this in our previous lecture, so last week, so in lecture 5b, that certain substances will undergo complete dissociation when they're in solution, all right? So a strong acid and a strong base will completely dissociate into its ions. Okay, so like I said, it's a strong electrolyte, complete dissociation in solution. So what that essentially means is that we have a lot of either H plus or OH minus floating around in that solution. Because we have a much higher concentration of those ions, our pH will be lower. Okay, so it's done. I'll go through this equation in a second, but just so you know now, strong acids and strong bases, they completely break up or completely dissociate into their two ions. So, in other words, they will have a much higher H plus concentration than, say, a weak acid or a weak base. A weak acid and weak base won't undergo that dissociation as much, okay, so it won't break up as much. It's much more stable to be kind of unionized or undissociated. So in comparison, we won't have a lot of H plus or OH minus concentrations in a weak acid or a weak base. Where that all ties in then is our pH equation down here. Now we're not going to be doing any calculations on this. I just put it there so you can see the link between the H plus concentration and your pH. So pH is calculated basically by taking the minus log of the hydrogen ion concentration in a solution. All right. So for example, okay, a strong acid, complete dissociation, we'll have a much higher hydrogen ion concentration here. Okay, so I'm just like there for you. Okay, so I'm talking about this, okay? A strong acid will have a much higher hydrogen ion concentration. If you input that into this equation, you'll end up with a lower pH result. Okay, so but just by putting that into a calculator, the higher the hydrogen ion concentration, the lower the pH will be. So we're in our acidic region up here. Similarly then, so we have, and I didn't include it because we're not going to be using it in the calculation, but to determine how strong your base is, you'd have POH there, and it would be minus log of the OH minus concentration instead. So we use this for acids, and then POH minus log of the OH concentration for bases. But in the exact same way that if we had a strong base, that's going to completely break up into its ions, okay? So we'll have a much higher OH minus concentration. Inputting that into this calculation there, the more OH minus ions you have, the higher that will be. All right? Is any part of that, do you want me to go back over any part of that? Because I know there's kind of a lot of information there. Or are you happy enough that I move on? Everyone happy enough so far?
Yeah, happy enough, Stitch. Thanks.
Okay. So just as a kind of a quick recap there, that you have your pH, okay? So the more hydrogen ions you have in solution, the lower your pH will be. The more hydroxyl ion, so your OH minus concentrations, the higher the pH will be. So you have strong acids on this side, strong bases on this side. You have neutral pH is where you have a neutral, so it's neither an acid or a base. All right. Okay, so just introducing where we actually come across these acid and base reactions. Okay, so like I said, we're going to see this in the lab. All right, so we're going to react an acid and base together. And what we'll see is the formation of what's called a conjugate acid and a conjugate base. So basically what a conjugate acid is, it's the chemical compound that remains after the base has accepted its proton. So remember that for the Bronsted-Lowry definition, what we're going to use, a base is a H plus acceptor or a proton acceptor. So the phrases proton and hydrogen plus, they're kind of interchangeable here, okay? So they mean the exact same thing. So when I say proton there, I mean a H plus. So this is the chemical compound that is remaining after the base has accepted that proton. So you can see it there, okay? So the base on our reactant side of the reaction, we have 2 protons. Once it reacts with the acid, it now has 3 protons. Here, here, and here. All right, so it's accepted that proton and it's become a conjugate acid. Similarly for your base then, okay, so this is the chemical or the conjugate base. This is the chemical compound that remains after the acid has donated its proton. So if I were to look over the reactant side, I have an acid here, one of my protons. During that reaction, it reacted with the base and it lost or donated that proton, or H plus. Okay, so you can see that there, the proton on this side has now been removed or donated to form a conjugate base. The reason we call it a conjugate acid and a conjugate base is that if I were to take that reaction and turn it on its head, so now these reactants or these products become the reactants. If I were to go in reverse here, that conjugate acid will donate a proton to become my base. So can everyone see that there, that if I were to just look at this compound alone, if I were to reverse the reaction, so now we're going this way, my conjugate acid will donate a proton to become my base. In the exact same way then, the conjugate base, if the reaction was reversed, so that will accept a proton to become the acid on this side. So we always look at the reverse, okay? So in the forward reaction, or in the one that we see here, we have an acid and a base to become a conjugate acid and a conjugate base. If we were to take that reaction and turn it on its head, our conjugate acid will behave as an acid, and our conjugate base will behave as a base. Is everyone okay with that, guys? Or does anyone have any questions on that so far?
Sorry, seriously, could you say the conjugate part again when it's going back the way?
Yeah, of course. No problem with that. Okay, so the forward reaction, it is what it is. Okay, so the acid and base react to form the conjugate acid and the conjugate base. So just imagine that I had taken this reaction and flipped it around. All right, so now my products are now becoming my reactants. So if I were to look at that reverse reaction that we call it, my conjugate acid here, okay, has 3 protons. When that reacts in the reverse reaction, it donates a proton and gives one up, so that it only has 2 over here to reform the base. Similarly then, the conjugate base, all right, so as it reacts, it will accept a proton from my conjugate acid. So it will start reacting. My proton will be accepted over here, and my acid will be reformed. Does that make a little bit more sense?
Yeah, thank you.
Perfect, no worries. Does anyone have any other questions on that so far, guys? No? Okay, so I'll keep going. So okay, so this is where it kind of comes into where you can see the application of the pH scale. All right, so I'll just go back here for a second. So as you can see, our pH scale, all right, so between 7 and 14, they're more basic or more alkaline substances. And then anything lower than 7, from 0 to 7, is more acidic. So you can see that here. Okay, so if I were to start in the middle, so at pH 7, we have human blood and tears. So I said that was around a pH of 7.4. Things like milk, our saliva, the rain that falls from the sky is very, very slightly acidic, but it's mostly labeled as neutral. Okay, so they have a pH of 7. So as you can see, when you become more basic or you're kind of increasing the pH there, so what we're going to be working with is sodium hydroxide, so that NaOH at 0.1 molar. That almost has a pH of around 13 to 14. So incredibly basic. Things like household bleach or household ammonia, so the examples I used earlier, the cleaning products, a little bit more, little less basic, okay, but still very, very strong. So you're talking maybe a pH of 12 to 13 there. Things like baking soda, they are much less basic, okay, so just hovering around the pH of 9. All right. Going in the other direction then, so becoming more acidic with each part. So black coffee tends to have a pH of around, I think it's around 6. So a little bit more acidic than neutral. Things like lemon juice, then they're actually quite strong acids, okay, so they can be anywhere between a pH of 3 to pH of 5. Gastric acid then, so that's the acid that's in our stomach that helps digestion. You're talking about a pH of maybe around 2. Okay, so incredibly, incredibly strong. And then what we're going to be working with then is hydrochloric acid. So we'll come across both NaOH and hydrochloric acid in our labs on Saturday. Okay. But as you can see here, they're incredibly strong. So either an incredibly strong acid or an incredibly strong base. Just to tie into what we've actually just looked at there, okay? So hydrochloric acid is very, very strong, all right? So that will break up almost immediately when we put it into solution, okay? So it'll become H plus and Cl minus. In the very same way then, when we add our sodium hydroxide into solution, that will break up almost straight away into OH minus and Na plus. So once we put that in, we'll have a much higher OH minus concentration for sodium hydroxide, okay? So that's what gives it its large pH value there. Our HCl, our H plus concentration will be much higher here in comparison to maybe some of our compounds in bananas or black coffee, for example. So that's why it has a much lower pH here. It all ties into our equation here. All right. So the higher this is, the lower our pH value will be. Okay, so just coming back to our litmus paper then, okay? So there's a couple of ways that we can measure the pH of a solution, and one of it being our litmus paper, okay? So again, it's pH indicator paper, so litmus paper is coated with this organic dye, and it will change color in the presence of an acid or a base. The one thing with litmus paper is that it doesn't give an accurate pH value. So we can't determine, well, okay, we have an acid, it turns blue, great, but we don't know what the value is. So that could be anywhere between maybe a pH 3 to a pH 7. We don't know the strength of the acid. So it's really only used as a first check to see, well, what are we working with? Is it acidic or basic? So like I said, we typically have 2 types of litmus paper. So red litmus paper is used to test for basicity or alkaline substances. So red paper will turn blue when it's exposed to a base. All right, so we'll dip it into solution. We'll take it out. If it turns blue, right, we're dealing with a base. On the opposite side then, we have blue litmus paper that we can add into a solution. We take it out. If it turns red, we know we're dealing with an acid. What's typically used in undergrad labs is that it's called a universal indicator paper. Okay, so it looks a little something like this, and it directly corresponds to the pH scale. All right, so I'll just jump back a little bit here. So the colors are kind of more, they're very universally known that red is very acidic, our purple colors are very basic, and then everything in the middle is between 0 and 7 and 7 and 14. So we'll have these in the lab, okay, and I will bring some in on Saturday to show you, and we can do that kind of first check anyway. But we can dip that paper into solution, and it will give us a very approximate reading of what the strength of that acid might be. So you have a strip of paper, you'll dip it in solution, you'll take it out, you'll see a range of colours, and you'll compare it to the colour chart on the actual chart. So it will give you an approximate pH, but definitely not accurate enough to say, well, this is the exact strength of that acid or the exact strength of that base. It's a very, very, very like first pass or first test. So how you'd actually do that then is that we can do this in the lab, okay? So we'll have our beakers of our acids and our bases. We can take a dropper, so we can take maybe like a small, maybe 1 or 2 drops of each of the solutions out, and we can touch the drop against the pH paper. What will happen then is that we will see that color change, okay, whether it be the blue to red or the red to blue, or we can use the universal indicator paper, but we can have a look and see what the approximate pH of the solution is based on just that quick little test. So what we don't do is that we never dip the paper directly into the solution. Okay, particularly if it's going to be used for an acid and base titration, because that organic dye that's on the surface of the paper is very subjective to dissolution in acids and bases. Okay, so we always take the sample to the paper and never the paper to the sample, because if that paper starts to dissolve in the solution, we can end up with contamination. Okay, so very, very important that we never dip it directly in. We take the sample to the paper. All right. So we can do this in the lab on Saturday. So guys, I will get onto the kind of pH meter because this is where we kind of see the much more accurate representation of the pH here. But I'm going to give you maybe a 10-minute break because I know there's an awful lot of information with the acid and bases. So I'll stop here just for about 10 minutes and then we'll come back to it then and we'll discuss how we'd more accurately determine the pH of a solution using our pH meters. Does that suit everybody? Brilliant
Yeah.
stuff. Okay. Perfect. Yeah. So if we're back by about maybe we'll say 6 o'clock and then we'll get started then on the rest of our slide deck. Right? Perfect. Thanks a million, guys. Right, guys, if everyone is ready, we might continue on with the slide deck. Everyone's happy enough?
Yep.
Perfect. Okay, just bear with me 2 seconds. I'll start sharing the screen. Brilliant, guys. So can you see the slide deck again?
Yep.
Okay, perfect. Okay, so like I just said just before the break, okay, so litmus paper is normally used to determine like a very rough estimation of the strength of an acid or a base, okay? So it will tell us whether the solution that we have is acidic or basic. It will give us a rough estimate of how much or how strong that pH is, but it won't tell us the most accurate value of that pH. So what we use here is what's known as a pH meter. Okay, so pH meters are used to obtain a much more accurate estimation of the pH. And it's done based on electrochemical potential. Okay, so if you recall back to lecture 5B when I discussed the kind of electrolyte strength, hydrogen ions can conduct an electrical current. And this is what's known as its electrochemical potential. Okay, so when hydrogen ions exist in solution, they can conduct electricity because they are in ionic form. Okay, so they're very freely mobile. They can pass through solution much easier than a compound could, and from that ability, they can conduct an electrical current through solution. So essentially, how a pH meter works is that it measures the electrochemical potential or that hydrogen ion concentration and how much of it is there and how well it can conduct that electrical current, and it compares it to an internal reference material with a known electrochemical potential. All right. So you'll see in the diagram here that we have a pH probe. Okay, so within that probe, there is a test sample or a test probe. So that will be used to determine the electrochemical potential of the test or the test sample. Whereas the other reference probe has this internal reference material on it, and that has a known electrochemical potential. What the pH meter essentially does is that it measures the electrochemical potential of your solution. It equates it to how much hydrogen ions are here, okay? Because we know pH is a measurement of the hydrogen ion concentration in solution. So it will measure the electrochemical potential. It will work out how much hydrogen ions are there that are resulting that electrochemical potential. And from there, it will do an internal calculation to work out the pH. So what we essentially have is that, like I said, we have a reference probe and a test probe. The probe contains an acidic solution that's enclosed by a glass membrane. Okay, so we'll see that in the labs on Saturday. So it'll be much clearer than this, and I can show you that on Saturday. But what you'll see is a glass membrane and 2 probes in it. And what that probe allows is for the hydrogen ions to pass through it. Okay, so we'll see that there. You'll see the 2 probes. The pH meters that we do use look very similar to this. Okay, so you'll see that we have a control panel that we can press to get a pH reading. And once we insert the probe into a test sample, it measures the difference in electrochemical potential. It then internally works out the hydrogen ion concentration and then the pH, and we'll see a very accurate pH reading appear on the screen that can then be printed and signed off. Okay, so it will give us I think it gives it nearly to 2 or 3 decimal places the pH value, and from that then we can very accurately determine how strong that acid or base is. So like anything in a lab, okay, so we have to make sure that the pH meter is calibrated before use, okay? And we use solutions called buffers, that I'll get to in a second. But pH meter calibrations are done using buffers of known pH, all right? So we essentially have what's called a 2-point calibration, all right? And it adjusts the meter at 2 different pH values, okay? So that it gives a very accurate response, more than 1 point along a linear equation, right? So we use 2-point calibrations an awful lot because it's a lot more accurate than just measuring the pH and calibrating based on one pH solution. So we normally do a 1-point calibration at pH 7, and then we either use a pH 4 or a pH 10 buffer, depending on the test sample that we're going to use. So for example, if we did the litmus paper test, right, we have either an acid or a base. If the solution turned out to be an acid, we would calibrate the pH meter using a buffer that is acidic. Okay, because obviously if our test sample is acidic, we don't need to calibrate on a basic solution. We calibrate based on an acidic buffer, normally a pH 4 buffer. So I will show you these in the lab. We have little sample cups containing a pH 4 or pH 7, pH 10 buffers. But if the solution is acidic that we're going to go test, we would use an acidic calibration buffer. So normally a pH 4 buffer there. When we have a basic solution, or if we did the litmus test, we found out it was basic, we would then use a basic calibration buffer, which is normally about a pH 10 solution. All right. So we will conduct the calibration based on what we need. So how this normally does it, and this is much better done as a demonstration, so I'll just talk through it now, and then in the lab on Saturday I will show you this directly, okay, because it's much easier to visualize this when you can see it in front of you. But the 2-point calibration is done a little bit something like this, okay, so you'll have that electrode, okay, so the electrode contains the probe, and you'll rinse that really well with deionized water. They're obviously made of glass, okay, and they're incredibly sensitive, so we dab it very carefully with tissue paper, just to remove any kind of remaining drops that might be on the electrode itself, okay, because that will obviously affect our pH reading if we have contaminants that are left over from a previous experiment. We don't excessively dry the end of the glass electrode, and this is because we don't want to break it, okay, so we don't want to be dabbing it excessively because we run the risk of damaging the probe. You then place the electrode into the pH 7 standard buffer, okay, so like I said, you have those little sample cups that will contain pH 7 buffer. You place the electrode into it and you allow it to stabilize for 1 minute. During that stabilization period, the pH probe is measuring the electrochemical potential, converting that into a hydrogen ion concentration, and from there it's calculating the pH for us. So during that 1 minute, our pH meter is working at the pH for us, basically. Once the pH reading is stabilized, so once that's done, it'll become up as ready, and it will give us the pH value. From there, then you rinse the pH meter as you would have done in step 1 there, dry it as you would have done in step 1, and you place it directly into the pH, in this example, our pH 4 standard buffer. And again, you allow it to stabilize for 1 minute. It's going to internally calibrate and calculate that hydrogen ion concentration, and then give us our pH value from there. So once it's stabilized here, we'll give you that ready value. You take it out, you rinse it and dry it as before, and then you can use it for a measurement. So typically what you will see is that it will come up, and again, it's much easier when you actually see it in front of you, but it will give you a slope value. Okay, so it will kind of calibrate itself anywhere between 95 and 105%. That's what we aim for. If there's a problem, you normally see a slope reading that's less than 95%, so you probably be around the 80 mark. If that happens, we'd have to recalibrate the pH meter. If we see the same problem, our buffers are not up to standard, so we need to use fresh buffer. But again, I will show you that in the lab on Saturday. But typically we aim for slope values between 95 and 105%. for our pH meters. So once all that's said and done then, so you actually go to measure the sample pH. Okay, so you've calibrated it based on what we have, you've done the litmus test, so you've confirmed whether it's acidic or basic, and then we can do our accurate pH reading from there. So again, you'd wash the electrode, little deionized water, and then a little bit of the solution you're going to measure. Okay, so this just makes sure that there's no residual water on the surface of the electrode. That would obviously affect the pH reading. Okay, so you wash it with a little bit of deionized water and a little bit of the solution that you're going to measure. Again, you would dry off the electrode gently, careful not to excessively dry it. And then you always make sure that the solution that you're going to measure is stirred before you take the pH reading. Because what can happen is that if it's not stirred, and particularly for samples that you'd have to solubilize or you'd have to dissolve in the solution, if you just stuck the pH meter in it without having it stirred, you run the risk of having in areas of higher H plus concentration than others. Okay, so it's not uniform. So what you do is you'd stir it first, make sure you have a nice uniform solution, and then you take the pH reader and then measure the pH. So in the exact same way you would have had with your calibration, okay, so you'd stir the solution, leave the electrode into the solution, allow it to stabilize. Once it's stabilized, it's calculating the pH value, and then you can record your value from there. Finally, then you take out the electrode, you wash it for the last time, dry it, and then you store it in the appropriate solution. So there's a couple here that we use to store it. What's really important that it's never stored in deionized water, okay? Because like I said, that the reference probe has a known electrochemical potential, okay? So that has hydrogen ions already present in the probe. What can happen is if you store it in deionized water, all of the H plus ions that are there will start leaching out of solution, and they will eventually go into the deionized water and be removed from the probe itself. Okay, so it's kind of done through osmosis. Won't get too much into that, but it essentially leaks it out or leaches it out of the probe into deionized water, and then the pH reference probe can't be used anymore. So we typically store it in buffers, ideally pH 4 buffer, but never in water. All right. Is everyone okay with that so far? I know I'm doing like a lot of talking through what you're going to see on Saturday, but just does anyone have any questions on that so far? All good so far?
Yep.
Okay, perfect. Okay, so this kind of delves into a little bit more of the dissociation of our strong and weak acids. Okay, so this is what I mentioned at the start when we were talking about our pH readings and why strong acids and strong bases give us very, very distinct, very low and high pH values, whereas our weak acids and weak bases tend to be more in the realms of maybe like for an acid anyway, around pH 3 to 5, and for our bases it's around maybe 8 to 10. And this is why it's all to do with the extent of dissociation. So if I were to show you this diagram, okay, so I wouldn't worry too much about these graphs here, but this just shows that we have a strong acid here. And then after dissociation, the acid is not present in its unionized form. Okay, so it's all present in its respective ions. So I wouldn't get too bogged down and seeing like H3O plus. It's the exact same thing as H plus. It's a hydronium ion or hydrogen ion. Okay, so they're interchangeable. So what this essentially means is that it breaks down our HA or acid, dissociates into H plus and A minus, and we should see them dissociate completely into those ions. Okay, so they will only exist in solution as H3O plus or H plus and our A minus or whatever that our other ion might be. Weak acids, on the other hand, then, and you'll see the difference in the graphs. Okay, so after dissociation, most of a weak acid or a weak base will remain unionized. Okay, it doesn't want to dissociate into respective ions. It's very stable and very comfortable to be in its unionized form. So what we'll see in solution basically is a combination of the acid or the weak acid or base as it is, the H plus ions, and our A minus anions. Okay, so you see the difference there. Strong acids, they completely dissociate. None of the acid in its unionized form is there. whereas a weak acid, it mostly exists still in its unionized form and hasn't really dissociated that much. So all in all, we would expect strong acids to have a much higher hydrogen ion concentration in comparison to a weak acid. So if I would just go way back, and again, I know I keep going back to this equation, but the more hydrogen ion concentration we have in solution, the lower the pH will be. Hence, stronger the acid. All right. In weak acids, it won't dissociate as much. We won't have as much hydrogen ion concentration in the solution in comparison to a strong acid. So our pH value will be a little bit higher in that case. So like I said, anywhere between maybe 3 and 6. Is that okay, guys? Is that making a little bit of sense?
Yeah.
Okay, perfect. Excuse me. Okay, so talking a little bit about our acid strength and how that relates to our conjugate base. Okay, so I mentioned the conjugate bases and conjugate acids already. It's essentially what this acid and base turn into once they react. So we have a little bit of an inverse proportionality here. Oh, sorry. Inverse proportionality to each other here, all right? When we have a very strong acid, so something like hydrochloric acid that we're going to use in the lab, that creates a very, very weak base or conjugate base. So what we say is that the stronger the acid, the weaker the conjugate base. And it's for this reason, okay? That a strong acid wants to dissociate, okay? It doesn't want to stay in its current form. It wants to break up into its respective ions. So it's much more likely to donate a proton or a H plus. Okay, it wants to get rid of it, it wants to donate it to the nearest base. So the stronger the acid, the more likely that's going to happen. Once the conjugate base forms, it doesn't want to accept that proton back. So it wants to remain as its ion. It doesn't want to reform its initial state or its initial unionized form. So what we say is the stronger the acid, the weaker the conjugate base, because it essentially doesn't want to take back that proton after it's donated it. On the other hand, then, if you have a very, very weak base, so like I said, weak bases or weak acids and weak bases, they don't want to be ionized. They don't want to dissociate. They want to stay in the unionized form. So once, and it's very unlikely that they will donate a proton, but if they do, and the conjugate base forms in this state, it will want to regain the proton as soon as possible. Okay, so it's not comfortable existing as a conjugate base. It doesn't want to be ionized. It wants to take back the proton and reform the acid. So the weaker the acid, the stronger the conjugate base for this reason. Okay, it wants to regain its unionized state, take back that proton, and remain unionized. All right. So you'll see that inverse proportionality to each other here. So when you have a strong acid, very, very weak conjugate base. When you have a very weak acid, a very weak or a very strong conjugate base, I should say. And it's the exact same for a strong acid and a weak base. A strong base, weak acid. All right. Is everyone happy enough for that, guys? You can see the kind of where the relationship is coming from there. No one has any questions on that so far, anyway.
Nope.
Perfect. Okay. So just to show you kind of a couple of examples, and I'm not going to go through all of these because I'll have your head wrecked, but it's just to show you where the conjugate pairs come from. So this is your acid with its conjugate base and your base with its conjugate acid. So when an acid donates that proton, okay, it becomes a conjugate base over here. So you can say that's a conjugate pair to each other. All right, the acid becomes a conjugate base. If the reaction were to be reversed, that base would accept a proton to become an acid. So that's a conjugate pair in that reaction. In the exact same way, your base will react to form the conjugate acid, so essentially pairs up. And if the reaction were to be reversed, your conjugate acid would donate a proton to become the base. So they just work in tandem with each other, I suppose, is the best way I could say it. So you'll see here in an example, okay? So when we react hydrogen and fluoride with water. So as hydrogen fluoride, so I'll just make that a little bit more clear. So hydrogen fluoride is my acid here, all right? So I need to look at how that actually reacted when it reacted with water. So can everyone see that as hydrogen fluoride reacted with water, it donated that proton. Okay, so it got rid of that H that's there in that reaction. So as it passed over and as it reacted with water, it became the fluoride ion or fluoride anion. It donated the proton. So in this case, this is my acid and this is my conjugate base. And you can double check that because if you were to reverse the reaction and the fluoride anion here, if that were to react, that would accept a proton, behaving as a base to reform that acid. In the exact same way then, if you looked at the water here in this case, so water as it reacted, once it passed over and it reacted with our hydrogen fluoride, it gained or accepted a proton here. Okay, so the water became hydronium, it accepted the proton, therefore the water behaved as a base and formed a conjugate acid on this side. So they're in tandem with each other. Is everyone okay with that, guys? Everyone can see where I'm getting that from, yeah?
I can see where you're getting it, but I'm not really getting the minus and the plus. I don't know whether we need to know that or not, but I'm just trying to figure it out as I'm going down.
Okay, so the minus and the plus just it highlights whether it lost or gained that proton. Okay, so I wouldn't be worried about it too much. Essentially, if I were to sum it up for you, anything that has a minus, that donated a proton. So it kind of goes back to our very first lecture that if you have more protons than electrons in the nucleus, it's positively charged. And if you have more electrons than protons, it's negatively charged. So I wouldn't worry about it too much. In this context, all you have to look out for is that anything that's negatively charged has donated a proton. So it behaves as an acid, basically. Anything with a plus on a reactant side, it behaved as a base. Does that make a little bit of sense?
Yeah, thanks.
Yeah, no bother at all. So I might pull up a couple of examples of this just when we go through the questions and things, but it's just so you're aware, anything with a minus, its tandem or its partner in that pair behaved as an acid. Anything with a plus, its partner behaved as a base. All right. Okay, so just moving on to our last little bit of this. So this is the last bit of theory that I'm going to cover on acid and bases because you're going to see this in practice in the lab. But I need to cover what's called a buffer solution. Okay, so buffer solutions are used to kind of maintain the pH at a certain value. All right. So these are particularly important that maybe if you were doing stability studies in a lab, all right, and a sample had to be kept at a pH value of a very certain value of a pH. Because if it strayed to maybe into more acidic or more basic conditions, it will affect the stability of the product. So buffer solutions are used an awful lot to just maintain the pH at a certain value. And buffer solutions are formed from a weak acid and its conjugate base. So it's a mixture of a weak acid and its conjugate base. And when I say resist changes in pH, it just means that it stabilizes the pH. Okay, so it won't change if a buffer solution is included. So you'll probably get sick of me saying this, but weak acids, okay, they won't dissociate in solution. Okay, so they only have a very, very small tendency to actually ionize and break up. So they're very unwilling to donate protons, okay? So it will exist more in its weak acid state rather than its dissociated state. However, they do undergo that reaction sometimes, okay? And I have a prime example of it down here. But when they do, okay, so sometimes they might donate that proton to become a conjugate base. And what we can see is an exact example of that down here, all right? So a buffer will only work if we have a certain balance between its weak acid and the conjugate base. So if we have too much of one, its buffering capacity is very, very low. We need to make sure that we have an exact balance between our unionized weak acid, and our conjugate base for weak acid. So for example, an acetic acid buffer is used an awful lot in the labs, okay, so to maintain a certain pH value. So we have a good balance between acetic acid in its unionized form and acetic acid in its ionized form there. Okay, so you can see the two, it's unionized here and anionized on this side. Okay, so it's undergone that dissociation I was talking about. So the reason this is set up as a buffer, okay, is that if I were to add anything to that solution, the two components will be able to react and change and basically maintain the pH at a certain value, okay? So if I add anything additional in, one of these two components is going to react in order to maintain that balance, so we don't see a change in pH. So for example, okay, so undissociated acetic acid, so on this form here, so the blue box, if I were to add in any base into that buffer solution, my acetic acid will neutralize it straight away. Okay, so the base won't increase the pH. Okay, so normally if you put a base into a solution, you'd see a huge jump in pH towards nearly 12, 13, 14, because you're adding the base into the solution. If you add it to a buffer solution, your weak acid will counteract that. And it will maintain the pH at a certain value because you're neutralizing the base that was just added in. Similarly then, if I had an acid, so if I add an acid into just maybe a solution of water, the pH will decrease dramatically, okay? Because the acid is going to break up into solution. We have much more H plus concentration floating around than we did, and the pH will drop significantly. But if I put it into a buffer solution like this, I have my dissociated acetic acid on the right. So if I add in any more acid, the acid is just going to react with my ion here and reform acetic acid. So it will counteract whatever I put in, essentially. Okay, so whether it's a base or an acid, if I keep that buffer solution in a certain balance, I know the pH won't change dramatically, and I can keep it almost constant. And like I said, this is incredibly important particularly for stability studies, okay? It's used an awful lot for kind of time stability studies where we're kind of keeping solutions for maybe months at a time. And particularly if our product starts to break down, the pH can change an awful lot. But by keeping it in a buffer solution, we resist that change as much as possible. So you'll often see that in the pharmaceutical industry that they use it particularly in stability studies, and it's quite important to kind of maintain a constant pH. For stability studies, you normally keep temperature, pH, protected from light, protected from certain agents. So this plays a very big role in that stability study. Okay, so just where you see where that kind of balance comes from. Okay, so what we want is 50% dissociation. That's what we aim for. So essentially, we want 50% of the acid to remain like this, 50% of the acid to be dissociated or ionized. Okay, so it will depend. So that balance I was talking about, we want 50% unionized, 50% ionized. Where that happens, and I'm not going to get too bogged down in this because you don't necessarily need to know this, it's just where this value comes from if you do see it, is that we have a value called the pKa value. All right. So what that pKa value actually means is that is the point where we have that 50% and 50%. So we have 50% of whatever our acid is in its unionized form and 50% of the acid in its ionized form. So that's what we aim for the buffer solution, whatever that value is. In this case, acetic acid and sodium hydroxide, it's around 4.76. All right. So I know that if I have the pKa of 4.76, I know the acetic acid will maintain the pH within a certain range of that. Okay. So if I add in an acid or a base, it's going to resist the change at that pH because it's at its pKa. Now, I wouldn't be getting too bogged down in how we calculate this or how we do it because it's not particularly relevant for this module. But I just wanted to let you know that if you did see this, that's what that figure means. It means it's 50. We have that balance that we need for this buffer solution to work. Is that okay, guys?
Yep.
Perfect. Okay, so I think that's everything that I'm going to cover this evening anyway, because I know there's an awful lot of theory in that. So I know we went from very calculation based to more theory based. So I'm going to leave the theory for now. And what I might do is I might just, well, I'll stop sharing the screen anyway first. Okay, perfect. Okay, so what I'm going to do is if you want to maybe take 5 minutes of a break, and what we'll do is I will pull up maybe 2 titration calculations, because I know we covered them at the very end of our last lecture last Monday, but we are going to be covering them an awful lot in the lab on Saturday. So I want to kind of maybe get practice with 1 or 2 of the titration calculations. So I'm going to pull up a couple of examples of that now. So if you guys want to take a 5-minute break, we'll come back, we'll do those examples, and then we'll leave it there for this evening, if that's okay. Does that suit?
Yeah.
Okay,
Yeah.
perfect. Right. So guys, if you just want to take a 5-minute break, and then we'll come back and we'll do those.
Yeah.
Yeah, you can all see that, okay, yeah?
Yes.
Okay, perfect. Okay, so I actually took this example directly from the 2019 exam. Okay, so this is very typical of what you'd see in an exam paper for this module. And this is probably the hardest of the titration calculations that you will get. Okay, so I thought this was a good example because it kind of covers, showing you the actual titration equation, the conversion of moles to grams, and then into a percentage weight per volume. And then we have a little bit of the pH at the end of it then. Okay, so what we have here then is a 50 centimeter cubed or 15 ml sample of vinegar, so an acetic acid solution, was diluted to 250 centimeters cubed in a volumetric flask. The diluted solution was then titrated against 25 centimeters cubed of 0.15 molar sodium hydroxide. The balanced chemical equation for the reaction is as so, that we have here, and the average titer value was 20.25 centimeters cubed. So first things first, we're going to calculate it in moles per liter. So we're calculating the concentration of, now it's a little bit confusing. So ethanoic is actually acetic acid, but I'm just going to label them both ethanoic. Geez, they really weren't nice that year. They were just throwing in random names for things. But anyway, we'll keep going. So I'm just going to highlight everything that we need for this. Okay, so for the moles per liter, you're going to highlight everything that's important. All right. So what sticks out automatically is our 25 centimeters cubed of 0.15 molar sodium hydroxide. Okay, so that's going to be important. We're going to need that. We're also going to need the average titer value that was here. And what we're looking for is the concentration of ethanoic acid in moles per liter. Okay, so you might recall from the molarity, the moles per liter is another way of saying molarity. Okay, so that's important there. Okay, so for all of these, for the titration equation, okay, so you'll know it's a titration equation because they'll reference that it was titrated against a certain volume. All right. So what you should be thinking is molarity of your acid multiplied by the volume of your acid all over the stoichiometric coefficient of your acid. Then we have molarity of your base multiplied by the volume of your base all over the stoichiometric coefficient of your base. Okay, so I would have covered this then in the stoichiometric notes. All right, so this is exactly what I've done in previous examples. So first things first, we're going to fill in everything that we know. All right. So the first thing is that it tells us to calculate the concentration of the ethanoic acid. Okay, so we don't know that yet, so I'm going to call that X. Your volume of your acid then, in this case, is your titer value. Okay, so 25.25 centimeters cubed. I know that, okay, because the volume that's listed up here is for the base. Okay, so my average titer value must be for my acid because I know that I only use 25 centimeters cubed of my base. So my stoichiometric coefficient here is 1. All right. And the reason I know that is by looking at my balanced chemical equation up here. So can everyone see that that is a 1:1 reaction? Okay, so my base here, do you know for my stoichiometric coefficients? Okay, so if there's no number there, I can assume it's 1. I'll just put it in here just so you can see it. That's going to be 1 mole of base reacts with 1 mole of acid to form my products. Okay. So in this case, I have no values there, so I'll just get rid of them. So it tells me it's a 1:1 reaction. All right, so that's what I fill in there. It's my 1. Is everyone see where I got that from? Yeah.
Yeah.
Okay. Okay, moving on to the other side of the equation then. Okay, so your molarity of your base is what we used. Okay, so in this case, it tells us we used the 0.15 molar solution of sodium hydroxide. So that's exactly what I'm going to fill in there, 0.15 molar. My volume on my base then is what I was told, so that's my 25 centimeters cubed there. All right. And then my stoichiometric coefficient on my base, again, it's a 1:1 reaction, so I'm just going to put in 1 there. Okay. I'm actually going to put a question mark there just so it's easier to differentiate there. Okay, so I'm looking for my molarity of my acid. So I need to get everything, I need to get my molarity of my acid on its own here. Okay, so which means I need to move my titer value across the equal sign. Right, so the first thing I'm going to do is I'm going to get rid of those ones, all right, because they'll cancel each other out anyway. So I'm left with this equation here. Okay, so I'm going to get my question mark there on its own because that's what we're looking for. Everything on the right-hand side stays the same just for the moment. Okay, so we still have 0.15 molar multiplied by 25 centimeters cubed. But when I bring my 20.25 centimeters cubed over the equal sign, it's going to divide on this side. Okay, so it's multiplying on this side. I'm going to bring it across and it's going to divide on this side. So we'll have something that looks like this. All right. So guys, just so I can know we're all on the right track, if you guys want to calculate this, and either if you want to just, you can say it out loud or you can write it into the chat, whatever you want. But just so I know that we're all working out the same value. And then I'll confirm whether we got that value or not.
How many decimal points do you want?
Let's say 3. Round up to 3 decimal places.
So it'll be 0.185.
Exactly, yeah.
Yeah.
So 0.185 molar. Perfect. Okay, so that's my molarity of my acid. Okay, so that's the first part done. Now, this is where they tend to catch you. Okay. You often see this as like the original solution. All right. We've just worked out, and if I just scroll back up here, see this sentence here that says that 50 centimeters cubed. Sorry, no, if I just highlight there. So 50 centimeters cubed sample of vinegar was diluted to 250 ml. So we need to take that dilution into account here. All right. So we need to work out what was in the original sample of that. So we diluted that. We made up a solution and we diluted it. So we need to work out what's in the original sample here. All right. And to do that then, so this is, I'm just going to write next to it that this is moles per liter. All right. So the easiest thing here, all right, is that you have a 250, you made that up in 250 mils in the volumetric flask. All right. Now, sample preparation and kind of standard solutions will become much more clear when we cover them in the lab. Again, it's something that's much easier to see when I demonstrate it rather than actually calculating it out here. But we took 50 mil of an ethanoic acid solution. We added it into a volumetric flask and made it up to the mark with 250 mil. So we added water to it to make it up to 250 mil. In this case, this would be the concentration if that was the original solution. All right, so we've done that correctly, but we need to take into account that that wasn't the original solution that they were asking for. We actually diluted that. So what I tend to do is that we have your volume of dilute solution. Sorry, no, so that's volume of dilute solution is 250 mil. My volume of my original was in the original solution was 50 mil. So when I work out the dilution factor here, so what I actually have to multiply my molarity by to work out what was the original, I divide one by the other.
0.5.
Okay, so it'll be 250 mil divided by 50 mil. Okay, so that will give you exactly dilution factor of 5, all right? Because I took 50 mil, added it to 250 mil in total. So I essentially diluted that 5 times, or by a factor of 5, all right? So, which means my original solution was 5 times more concentrated than it was in the dilute solution. So I'm going to multiply that by 5.
0.925.
Exactly. 0.925. And that is my original, so moles per liter. And I'm going to put original in brackets there. Oops. Original in brackets. Okay, so this one is your dilute solution. Okay, so just as a bit of a recap there, we did the titration equation, we got the molarity of the dilute solution, which is great. The question asked for the original solution, so I need to take into dilution factor into account. All I do there to work out the dilution factor is divide my dilute solution by my original. It normally works out as a whole number, okay, so they won't be giving you something too complicated that you're talking about dilution factors of like 3 or 4 decimal places here. So my dilution factor was 5 in this case, and then all you have to do is multiply it by the molarity that you've gotten. Is everyone okay with that, lads? Everyone can see where that's coming from?
Yeah.
Okay, so that is, I'm going to call that part 1. So just so you can see where this is coming from in the exam, all right? So by working out that would have gotten you 5 marks in total, all right? If you didn't do the dilution factor, okay, so if you missed this part and you just worked out the molarity of the dilute solution based on the dilute solution, that would give you 2.5 marks anyway, all right? So I wouldn't be worried that if you forget how to do the dilution factor part, because you will get half marks for that part if you just simply do the titration calculation. The additional 2.5 marks comes from the dilution factor part. All right, so spinning back up to my question here then, so it tells me to work out, it also asks me to work out in grams per liter, all right? So this is where, and you're going to be sick of me saying this, that triangle comes into play here, all right? So if I look at what my molarity was, 0.29 or 0.925 moles, all right? That's another way of saying moles per liter. The question asks me that I have to get this in grams per liter. So with any of the moles to mass or mass to moles calculations, and again, you're going to be sick of me saying it, but you need to work out the molar mass of what you're working with. Okay, so this should be your first step, no matter what the question is. So you'll see the kind of continuation of what we're doing already. We have the moles to mass conversion. You're using the molar mass, using the triangle. We'll work out a certain equation that we have to use, and then we'll be able to convert it from there. So in this case, we're looking at ethanoic acid. Okay, so it's the C2H4O2 there. I'm just going to copy that down just so you have it. And we're going to do that in the exact same way we've done it in the labs and in lectures so far, okay? So I'm going to write down all of the elements that I have. In this case, I have carbon, hydrogen, and oxygen. So carbon from the periodic table, okay, has 12 grams per mole. And that 2 there tells me I need to multiply that by 2. I have 2 carbon atoms. In the exact same way then, so we have hydrogen. So 1 gram per mole from the periodic table multiplied by 4. And then my oxygen then is 16 grams per mole taken directly from, 16 grams per mole taken exactly from the periodic table and multiply that by 2 for my 2 oxygen atoms there. Okay, so I should have up here is 24 grams per mole. 4 grams per mole for hydrogen in total. And then 32 grams per mole for oxygen in total. Okay, so I'm just going to add all of those up together. Okay, so what you should be getting here is 24 plus 4 plus 32. You give us a total of 60 grams per mole there. And again, guys, if you only got that far, that would be worth 2.5 marks of that 5-mark portion, right? Because it's worth 15 marks in total, so far we have 7.5 marks done and dusted. Okay, so your step 2 then, okay, so we worked out the molar mass, okay? We know we have 0.925 moles per liter. So we have 0.925 moles per liter. We have our molar mass now, okay? So just excuse me a second, I'm just going to go grab this. All right, so looking at our triangle here, okay, so I've worked out the molar mass of what I have. So I have the molar mass. I have the moles in the question. Okay, so I've just worked out that 0.925 moles. So can anyone suggest how I calculate the mass then?
You have to multiply that.
Exactly. Okay, so your mass is going to be your moles multiplied by molar mass. So in this case, it will be our 0.925 moles multiplied by 60 grams per mole. And that will give us, so 0.925 multiplied by 60.
55.5.
Exactly, 55 grams per liter in this case. And that is another 2.5 marks. All right. Is everyone happy enough with that so far, guys? You can see where I'm getting those values from.
Sorry, seriously, no, the first part.
Up here, is it?
Yeah, where we got the moles per liter times 5.
Yes.
How can we multiply that if we're looking for a smaller volume of the solution?
Because the original solution is much more concentrated. All right. So if you can imagine, right, when we added that 50 ml of the concentrated solution in, all of that acetic acid was sitting in a 50 ml portion. All right. When we added the 50 ml into water and then made it up to 250 ml, whatever was in that 50 ml kind of spread out among the 250 ml. So it became much more diluted. By multiplying by 5, we scale it back and then we know how concentrated it was in the 50 ml portion before it was allowed to kind of spread out and be diluted. So that's why we multiply it. Does that make a little bit of
Okay.
sense?
Yeah, just in my head, we would have divided because we were looking for a smaller volume, but that makes sense now. Yeah.
Okay, perfect. All right, guys. So the last little bit of that then, it just asked for. Sorry, no, I'm just going to highlight what we have. Okay, so we have moles per liter, that's done. We have our 55 grams per liter, that's done as well. So the last part asked us for, the percentage weight per volume. Okay, so this often comes up that it asks you to do the concentration in 3 different ways. So we have 2 of the 3 done. So this one asks for percentage weight per volume. So whenever you see this, guys, this means it's another way of saying grams in 100 ml. Okay, so no matter what you're working with, if you see percentage weight per volume, it automatically means grams in 100 ml. So if I were to look at the grams per liter there, all right, so I know I have 55 grams of acetic acid per liter, which is another way of saying 55.5 grams in 1,000 ml. Okay, because a liter is 1,000 ml. So I'm nearly there. Okay, so I have 55 grams in 1,000 ml. If I want to get 55 grams in 100 ml, I need to divide by 10. Or you could do it, we'll do it the long way just so I can show you. The best way to do it is to simplify it as if you had 1 ml. All right, so I have 55.5 grams in 1,000 ml. If I wanted to work out how much grams were in 1 ml, I would divide by 1,000. Okay, so if you divide 55.5 by 1,000, that's another way of saying I have 0.0555 grams per mil. So can anyone suggest what I'd have to do to work out how much I have in
We have to
100?
multiply by 100. Yeah, now we have to multiply by 100 because that's what we're looking for.
Exactly, yeah. So it's multiplied by 100.
That
So
gives
what's
us
that?
5.55.
Exactly. 5.55 grams in 100 mil. And that's 5 marks for that one then. All right, so again, that is a very typical question. So I took that directly from the 2019 paper. All right, so that's a very typical question of what you'd expect for your titration because it ties in an awful lot of the theory that you would have covered for the calculations. All right, but again, it's the exact same steps each and every time. So what they'll ask you to do, it'll essentially start off as a titration calculation. So that's your MAVA over A, MBVB over B. We'll go through that an awful lot on Saturday, so we'll get more practice with that. That will give you a value in moles per litre. They will often throw in that dilution factor question. All right. Look, even if you can't get the dilution factor, I would continue on with your dilute solution. The worst that will happen is you'll probably lose maybe 2 or 3 marks if you continued on. Because you're doing the steps correctly, but you've just missed one little step. All right. So even if you got down that far and you couldn't do the dilution factor, I'd recommend just keep going with the dilute solution calculation. All right. So you'll work out moles per liter. They will definitely ask you to convert to grams per liter because it shows off your knowledge of converting mass to moles. I'd recommend you work out the molar mass straight away because there will be marks going for that. Then you convert it into grams per liter as we did. And there's often a little step at the end then where you have a further conversion into a certain percentage weight per volume. And that's that then. Is everyone happy enough with that, guys?
Yeah.
Okay, so I won't go through it now, right? But on the 2019 paper, so that was the first part and that was worth the most marks. Okay, so that was question 5, part A. So 5 marks for each one of the parts there. And then there was a 10-mark question and it covers what we what we did this evening. Okay, so part B was made up of two different parts, part 1 and part 2, 5 marks each. And it looks something like this. Okay, so it says acetic acid is considered a weak acid, whereas hydrochloric acid is a strong acid. What do you understand by the underlying terms? So I'm just going to highlight them there. Oh, no, sorry, wrong ones. Okay, so they often follow up the titration questions with things like this. So it's kind of like your understanding of what the acids actually are. So for that then, a weak acid and a strong acid, you're looking for the differences between them, all right? And what they're looking for here is the dissociation of them. So again, a strong acid completely dissociates into its ions, does not want to remain in its unionized form, and will readily donate a proton to undergo the acid and base reaction. Weak acid is the exact opposite. Okay, so weak acids want to remain unionized form. They will only partially dissociate into their ions and therefore will not donate a proton as readily. Okay, so that's what they're looking for there. If you're looking between the difference of a strong and a weak acid or a strong and a weak base, you should be thinking about dissociation there. Then you would define the pH, okay, so what the pH actually tells you. Okay, so that's the strength of the acid or base there. And then how would you determine the pH of an acid? So you could go into kind of like, well, you do use litmus paper on the sample. So they're actually asking you for the procedure there. So you test it using litmus paper, indicate whether it was an acid or a base. To work out the exact measurement or the exact pH measurement there, you would use the pH meter. And that's what you'd be looking at discussing there. All right. So they tend to follow up the titration calculations with the theory on acid and bases. So they tie directly into each other. But again, we'll see much more practice of that in the lab on Saturday. Is that okay, guys?
Yeah.
Perfect. Okay, so I'm